she's going to tell us how to formally verify that closures don't take up more space than they should.
Hello, everyone. So formally verified compilers such as ComCert and KKML have been some of the most impressive results in formal verification. So the problem is that we, as programmers, write in high-level languages that we understand very well, and we reason about them formally or informally. So compilers then translate these programs to low-level languages that are really hard for us to understand, let alone reason about it. So a formally verified compiler bridges that gap by guaranteeing that the behavior of the generated program matches the behavior of the source program. So if we know that our source program has some extensional property P, then we can guarantee that our compiled program will also have this extensional property P. And by extensional, I mean properties that refer to the result of the computation. For instance, if our source computes 42 factorial, then our target will compute 42 factorial. Oftentimes, though, programmers reason about intentional properties of programs, such as running time and space. And in such cases, formally verified compilers, at least with a standard sense, have no way of guaranteeing this result for the target program. Which is really unfortunate because compiler transformations may actually leak resources. And what's even worse is that there are people on the internet complaining about it. So let's talk about JavaScript. JavaScript's V8 engine uses a closure representation that is not safe for space. And this might make the asymptotic behavior, the behavior of the program asymptotically worse than we expected. So the question is, what can we, as programming languages researchers, do about it? Well, we can extend our compiler correctness statement to include preservation of time and space consumption. And the good news is that there are already extensions of ComCert that extend the theorem to memory preservation. However, this problem becomes much harder when we talk about higher order memory managed languages. And the reason is that in these cases, it's not enough to reason about the amount of allocated and deallocated space, but we must explicitly reason about the heap objects that are simultaneously live during the execution of our program. And closures that are used to implement first-class functions change the liveness of objects in the heap, perhaps much more than any other transformation. So towards this end, we present the first formal proof that closure conversion is safe for space. So this result is implemented and verified in Coq, and our transformation is part of the Certicoq compiler. And the two key technical ingredients that make this result possible is setting up a profiling semantics to give a cost model for the source and target languages, and a logical relation framework that allows us to reason about intentional properties in a principled way. And it turns out that because of this ability to track resources, we can also reason about divergence preservation, and also that memory consumption is preserved for diverging programs as well. And divergence preservation is something that traditional logical relations cannot handle without complex machinery. So I'll briefly talk about Certicoq. Certicoq is a verified compiler for Galena, and it's implemented and verified in Coq. And it translates Coq to ComCert CLite that can be then compiled with ComCert in order to produce a verified assembly language. Some of the transformation that Certicoq employs is type and proof erasure, and also conversion to continuation passing style. So then, in continuation passing style code, we perform closure conversion. And after closure conversion, all functions are closed. We can host them up to the top level, and then the program enjoys a straightforward translation to C. Our compiler also features a verified garbage collector, which is implemented in C and verified in Coq using VST. So let's talk about closure conversion. Closure conversion is used to implement static scoping in languages with nested function, and it eliminates free variables by explicitly constructing a closure environment upon function definition, which is passed as an extra argument to functions. So in particular, consider this little piece of code. F has two free variables, z and y. So closure conversion will first construct F's environment, will consist of z and y, and then it will modify the function definition so that it takes an extra environment argument, and then it will access the environment to find the values of free variables. Then the environment will be packed together with the code in order to form a closure pair. Later on, at application time, we can project out the code, we can project out the environment, and we can apply the code to the environment and the original argument. So in the first line of this closure converted code, we implicitly made a decision about how to represent the closure environment. And this is a very critical design decision in closure conversion because and compiler engineers put a lot of effort in optimizing these representations for different aspects of the code, such as closure creation time or access time to free variables or space usage. So let's go through some of the most standard closure environment representations. So consider the situation. We have a function f, it has some arguments, and then it does something with some free variable L. Then we define a closure inside fg that has, again, some free variables, and a closure h that has, again, some free variables, and finally f returns the closure h. So in flat environment representation, the environment of its closure will have exactly the free variables that appear free in the function. So for instance, f will have free variable L, and then free variables u and w. And this is nice and straightforward, but there is a problem. There is some redundancy in our environments. And it would be nice if we can do some sharing in order to avoid storing free variables more than once. And linked closure representation attempts to solve this by only storing the free variables that appear free in a function, but not in the immediately enclosing function. And instead, it adds a link to the closure environment of the immediately enclosing function so that the function can access the remaining of free variables. This is nice, we save some space indeed, but there is still some room for improvement. Z is still stored twice. So yet another option is to share the environments of closures that are defined within the same scope. So this here would mean that Z and H have the same closure environment, which holds the union of their free variables. And yay, that looks good. Our closure conversion transformation seems super optimizing for space, so we can go home happy. But not so fast. So this is the representation that's used by JavaScript V8 engine, and it turns out that it's not safe for space. So why? Because consider this example. So it might be that the lifetime of H can extend longer than the lifetime of F. So H might be alive in our program longer than F does. However, by keeping the link to the environment of F, we necessarily keep alive in our program the free variables that appear free in F but not in Z, and therefore this space cannot be reclaimed by the garbage collector. Now, if the space is not constant, this might make the space behavior of our programs asymptotically worse. So, and that's, of course, not good. However, flat closure conversion is safe for time and space, and this is exactly what we proved for our compiler. So in particular, we proved that the time and space cost of the target is upper bounded by some linear function of the source, of the cost of the source. We profile time and space using profiling semantics. Our semantics takes as input a configuration which consists on a heap, an environment, and an expression. And in order to account for time, it is fuel-based, meaning that it can throw some out-of-time exception if there are not enough steps for execution. Otherwise, it will just unwind the fuel by the cost of the evaluation step. And it also accounts for the space consumption. So what are our cost models for the source and target? So in the source, the time cost model is almost the same with the target, and the only difference is that in the source function definition incurs cost proportional to the number of its free variables to account for implicit environment creation, whereas in the target, functions are closed, closure environments are explicitly constructed by the code, so function definition incurs generic cost. So our space cost model changes a bit between the source and target. So in particular, in the source, we keep track of the maximum size of the reachable heap, which conceptually corresponds to an ideal garbage collector running after every evaluation step. And in the target, instead of that, we profile the size of the actual heap, and we allow an ideal garbage collector to run upon every function entry, which is the strategy that we employ in Certicog. So this way, we do not only prove that closure conversion is safe for space, but also that this particular garbage collection strategy is safe for space. So our top-level theorem says that if a program closure converts to some other program, and if the source program evaluates to some final value in heap, then the closure converted program will also evaluate to some final value in heap. The two final values in heap will be related to each other. And in addition, we know that the time cost of the target will be upper bounded by some constant factor times the time bound of the source, and that the space bound, the consumed space of the source will be upper bounded by the space of the consumed space of the target will be upper bounded by the consumed space of the source, plus some function which is linear in the size of the input program, and intuitively keeps track of the maximum amount of space that the two heaps can diverge. So a few words about our proof. So we use a logical relation that roughly looks like that. It relates to input configurations, and it additionally is annotated with some pre and post condition. So we use the precondition to enforce some relation on our input configuration. In particular, in our proof, we use to relate the sizes of the two input heaps. And we use the post condition to enforce the properties that we want to enforce on our resource consumption. Our logical relation is step indexed, but we also have an additional index, which is the heap index and bounds the heap depth. So decoupling this from the step index is not necessarily for well-foundedness. However, it's a nice technical device that gives us flexibility in proving properties about the related heaps. And what's new about it? It's that we can reason about consumption preservation, and exactly because of that, we can also reason about divergence preservation and memory consumption for divergent programs. So to sum up, we presented the first formal proof that closure conversion is safe for space. Our results are mechanized in Coq, and our transformation is part of the Certicog compiler, and we set up a general logical relation framework to extend reasoning to intentional properties. So in the future, we would like to extend this upwards and downwards. Extending upwards would mean that we would like to propagate time and perhaps space bounds through Certicog and connect it to some Coq source logic. And extending downwards, we would like to connect it with our C translation and our concrete garbage collector implementation. And by this way, we prove that our abstract garbage collector semantics are sound with respect to the concrete garbage collector implementation. Thank you very much.
Yeah, so the first question is from Slido. What about linked shared environments with black holing?
I've never heard about it.
Yeah. No, please wait for the mic.
Okay. So you said you have a proof that the conversion is safe, but you've also shown that applying closure conversion, as is the case in JavaScript, you can get memory leaks.
Mm-hmm.
So what I didn't quite get is, does your implementation say we don't have that memory leak? And if so, what is the mechanism by which it avoids that specifically?
We use the straightforward representation. We use the straightforward closure representation, which is not optimal for space consumption, but is safe for space. JavaScript V8 uses the representation that attempts to save space, which is linked plus shared, but this is not safe for space. So the difference is that our closure conversion transformation uses a simpler but safer space closure environment representation.
Do you think that it could be extended to go to more complex?
I think it could be extended to verify like optimally linked closures, such as these of Zhong-Sao, but not linked closures because these are not safe for space. So we could perhaps prove something about unsafe closures, but it will be much weaker than that.
In the back.
So you mentioned that in your logical relation you have the depth of the heap. Does it mean that it prevents you from having recursive structures in there, or?
No, it doesn't. So this is exactly because the structures in the heap can be circular. So we want to index it in order to handle circularity in the heap.
Another question on Slido. Could you say a bit more about how you define the space usage of a program in the source semantics?
Mm-hmm. So we have a big step, operational semantics, and at every rule we check what is the current size of the reachable heap, and we take the maximum with the maximum so far and the maximum now. So yeah.
Thanks. So yeah, as a former V8 engineer, I just want to say something in defense of the design choices there. So of course we are fully aware that this is not safe for space, and the reason of course is all the environment entries in JavaScript are mutable, right? So to do like this other representation, you would need an extra indirection, an extra allocation for every single variable, which would basically blow up the space used by closure environments by a factor of 3 or 4. So, and when you measure real programs, you quickly figure out that's actually worse cost to pay than being safe for space. So just as an explanation for why we did it.
Thank you very much.
More question from the floor?
Can you go back to slide 13?
13? Mm-hmm. This one?
No, maybe 12? Yeah, this one. Okay, sorry, it was 12. Okay, so I have two small questions on this. So first, could you give some intuition why one of the bounds is multiplicative and the other one is additive? I feel like this is, I don't know.
So basically for the time bound, the constant factor is the maximum overhead that closure conversion can add for every constructor of the language. So assume that we have a free variable. In order to handle this free variable, we should perform some projections from the environment, but this is some constant time operation. So this is just the maximum of constant time overhead that closure conversion might add to the code. However, for the space bound, this is an additive factor because, so we call garbage collector upon function entry. And our code is continuation passing style. So our code can have only a bounded amount of allocation until the next function is called, the garbage collector runs again, and then the relation on the heaps is established again. So this additive factor captures exactly the amount of allocation that can happen before the relation on the size of the heaps is established again.
Okay, and then a tiny thing. I'm a little concerned that your cost space depends on E.
Okay.
I mean, it just seems a little concerning because there always is going to exist a cost space of E that verifies this, right? You give it an M2, you give it an M1, you can always find the cost space of E. So what's exactly?
But I'm not sure I understand that. But so the intuition is that for this is a constant upper bound given a source program. So for every source program, the time consumption of the target is upper bounded by some by the space consumption of the source plus some constant.
Okay, that makes sense then.
Because for its source this is a constant.
Any other questions? Oh, well, then, thank you. And next speaker set up.